Hello, I'm Past Paper Guy. I'm going to be solving the GCSE Electronics by WJEC, the 2018 E1 paper. In the section below, you'll see a link to this paper. I strongly recommend that you give it a go and then have a look at this. Question 1. So this is the dead easy recognizing things question. So that's a transistor. This is a diode. And this is a push switch, push to make switch. Here we've got to sort all of these into these categories. So if we just start from here, we have an OR gate is a process, a temperature sensor would be an input, a light sensor would be an input, a transistor switch unit, that would be a process, a delay unit is a process, a solenoid unit, that would be an output, because it might control a door or something, or a lock. A buzzer unit, that's an output. A switch is an input, and a lamp is an output. Question 2. Standard question using Kirchhoff's laws. So what's the value of V1, this voltage here? Well, from here to here is 3 volts. So to get from 3 volts to 9 volts, we need 6 more volts. So it's going to be 6 volts. What is the value of I3? That's this one here. We've got 7 milliamps coming down here. If 2 go off that way, then 5 milliamps must go on that way. What's the value of V3? V3 is in parallel with V2, so it's got to be the same, so that's 3 volts. And what's the value of I4? Well, that's all the current joined back up again. That current there joins with that current there, so it's 2 plus the 5, which is 7 milliamps, which has to be the same as the current entering there. Here is a logic gate. Number all the pins on the diagram. Blimey. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Tick the boxes for the input pins for gate B. Well, the input pins for gate B will be 1, 2, and 13. Tick the boxes for the output pins of gate A. So that's going to be that one there, 8. Draw the correct logic gate to match the name in the table below. An AND gate is that one there, and the NOR gate is an OR gate with a circle on the end, like so. Question 5. This is just a basic learning one. We have the gate, the source, and the drain, so it's this one here. Here we have a resistor, orange, white, and red. We need to find out what these colours are. So this is easy as looking up. Orange is 3, white is 9, and red is 2. So that's the answer. So it's a 3900 ohm resistor. The following shows a solenoid connected to a power supply. Here we want to calculate the power of the solenoid in watts. So P is equal to I times by V, which is equal to I is 8 times by V is 25. So we want 8 times by 25. It's that, which is 200. 200 watts. Question 8. The following analog sensing unit is part of a security system. So we've got an LDR there and we've got a variable resistor there. Name the component labeled X. So that's the LDR. Vy, this one here, is equal to 2 volts. Circle the correct voltage across component Vx there, like so. So that is got to be 2 volts plus 8 volts gives you 10 volts. So it's got to be 8 volts. What would happen to the value of Vy if the resistance of component Y was increased? Well, that would increase it. If it's got a bigger resistance, then its share of the potential would increase. So Vy would increase. If the resistance of the value component Y and the power supply voltage remain fixed, what would cause the output voltage Vy to decrease? Well, for Vy to decrease, this resistor has to get bigger, and so therefore you want because the light response of this resistor, so this is bright, this is dim, this is R, looks like this. To increase its resistance, you want it to get darker, so if it got darker, the LDR resistance would increase. This reduces Vy. Question 9. So this is the big planning of a subsystem 1. A garden centre grows a number of plants from seed before making them available for sale. It is important that the soil remains moist while these seeds grow into young plants. The system is needed to monitor the conditions of the soil during daylight hours. It continuously pulses a warning LED, so continuous pulsing, so that's going to be an A stable, a warning LED on and off when the soil is too dry. Okay, a number of sensing subsystems are available to use with the following specification. A light sensor outputs a logical 1 when it's in daylight and logical 0 when it's nighttime. So we want it to be daylight, don't we? Because it said so somewhere up here. Here we go, during daylight hours. A temperature sensor when it's cold and when it's warm. I don't think we care about the temperature. And a moisture sensor that's 1 when it's wet, and that's okay. And 0 when it's dry, that's not okay. Okay, so let's try and get these two ones down. So we want something that triggers when it's too dry. So we want a moisture sensor, but we want to give it a 1 when it's too dry. So we're going to follow it by a NOT gate. So we've got two boxes here. So a moisture sensor and a NOT gate. Now, the other one that we want here is to find out whether it's in the daylight. So we want a light sensing unit here. Now both of those have to be true in order for this to follow through to here. We want it to be both dry and daylight, so we want an AND gate here. Now we've got a pulse generator here, and we've got the when it should be triggered. So we want to, if we look at this, if you think of this as the pulse generator and this one here as point X, then when this is 0, we want the output to be 0, and when this is a 1, then we want the output to be whatever the pulse generator is. So that's a 0 and a 1. So that there will follow this pulse generator if this is true here. So in order to do that, if you look at that gate, that is an AND gate there. So that's an AND gate. And then the last thing that we want here, before the LED, maybe a transistor switch unit. Always a good bet to put a power amplifier in before the final output. And that gives us the answer. Question 10, circle the logic gate that has the following truth table. Well, 0, 0, 0, 1 would be an AND gate. This is the opposite of that, so that's a NAND gate. Circle the logic gate that outputs a logical 0 only when both inputs are at a logical 0. So that's that gate there, isn't it? That's an OR gate. I think it's often easier to try and, instead of trying to understand the words here, just to draw a truth table. Right, here we look at X, and we'll see that X is just not of A. So we just need to put a NOT gate in there. If we look at Y now, Y is the opposite of B. So that's just a NOT gate for Y as well. And then what I've done here is I've redrawn this truth table here in the normal order. And so you put 0, 0 gives you a 1, and all of these combinations give you a 0, and that's a NOR gate. So a NOR gate goes here, like so. Circle the single gate that can be used to replace the combination above. Well, we just need to look at Q compared with A and B, and we'll notice that 0, 0, 0, 1 is an AND gate combination. So that's an AND gate, like so. Question 12. The logic gate below contains some NAND gates that are redundant. Circle the redundant gates. So we're looking for ones that are configured as NOT gates like this that follow each other. So those two and those two, like so. That one doesn't follow another one, so, and nor does that one, so you can't cancel either of those. Here we have some combinations of resistors. We need to add these up because they're in series. So that's going to be 49.7K. This one, they are both the same, so you can just divide it by 2. So that's 68 over 2, which is equal to 34. So it's 34 kilo ohms. This one we need to use the equation. There are various equations you can use. Because it's got 2, we can use the product over the sum. So it's R1 times by R2 divided by R1 plus R2. Now, as long as we leave everything in kilo ohms, the answer will come out in kilo ohms. So we can do 3.6 times by 18 divided by 3.6 plus 18. And then we will need a calculator for that. So we've got 3.6 times by 18 divided by 3.6 plus 18. Make sure you put your brackets in correctly. And that's equal to 3 kilo ohms. 3.0 kilo ohms. Question 14. Select the correct truth table that corresponds to this Boolean expression. So not A and not B. So we're looking for when both of these are low. This should be high. So it's not that one, not that one. It's this one. And here we're looking for not A and B. So this is, if we De Morgan that, we get A or not A or not B, because we break the bar there and we change the sign. So if either A is low or B is low, we'll get a high output. So there's A's low gives us highs, there B's low gives us highs, and when they're both not low, then we get a low there. So it's that one there. Right, here we have some NAND equivalents. We need the NAND equivalent of a NOT gate. You just should know this off by heart, really. The NAND equivalent of a NOR gate. Well, a NAND gate is easy. We'll do that one first. So that's an, let's say it's easy. Messed it up. There we go. It's a NAND gate followed by a NOT gate. And then the NOR gate is, if we use De Morgan on that, we get A, not A, and B like that. And then we need to put a double inversion on there to make it out of NAND gates. So we're going to need that for A and B. And then they're coming together with that one there. So we've done that much. Then we need that final inversion there, which is that one there, which is the exact same as that one there. So you can either learn that off by heart or you can work them out, as I do, when you need them. Question 16. So here we have a voltage divider, and we are trying to find out what V out is. So this is the potential divider equation. V out is equal to V in times by R2 over R1 plus R2. And again, as long as these are the same units, the units will cancel each other out. So the total voltage in is equal to 10. R2 is 4.7 divided by the sum of these two, 4.7 plus 6.8. which is 11.5, isn't it? So it's this one here. Calculate it. So we need to do 4.7 divided by 11.5 times by the 10 is equal to 4.08695 ... So that's 4.09 volts to 3 SF. You could put it to 2 SF if you like. B. The following circuit uses a variable resistor. It's actually a potentiometer, but we'll let them off. Can also be used to provide a reference voltage for a comparator. Okay, give two advantages of this compared with this. Right, well, it can be changed is the first advantage. So the out can be changed. And tuned to get any value. I guess the other advantage is that maybe you can go as low as 0 and as high as 10, whereas this one you can't get as low as 0 or as high as 10. So you can get as low as 0 volts and as high as 10 volts. Question 17. The following incomplete circuit shows a comparator to be used to switch on a warehouse heating system when the temperature gets too cold. Okay, draw the components necessary on the circuit to provide a voltage of 3 volts at the inverting. So we want 3 volts there. So we want this to be a potential divider. And we've got 15 volts, so ideally we'd want numbers which added up to 15 here, 3 here, and 12 here. And lo and behold, we can do that. So there's 3K there and 12K there. So if you use the potential divider equation on that, you figure out that that was 3 volts there. Draw the components necessary on the diagram to provide a rising voltage at the non-inverting input when the temperature falls. So the temperature, oops, that's the resistance. The resistance as the temperature changes on a thermistor looks like that. So as the temperature falls, we've got falling temperature here. That means the resistance is rising. And we want a rising voltage here. So we want to put it in this one here. That means as this one gets bigger, this voltage will get bigger. As the temperature falls, this one gets bigger, so this voltage gets bigger. And then well, it doesn't really matter what you put here now. I'm going to put the 10K here. How would you alter the circuit so that the temperature at which it switches on could be adjusted? Well, that was this question here. You do what you do in 16B. Put 16B in. So use a potentiometer to allow you to vary the voltage V minus. So C diagram. So we would have this, and this would go in here instead of that. So this is part C. there. Question 18. What's the voltage drop across the resistor here? So we've got 2 volts there, so we need 4 volts across there. Select the correct equation to determine the value of resistance. So R is equal to V over I, which is going to equal, remember to use the voltage across the resistor, not the full 6, divided by I is 25 milliamps, so that is 0.025. But if we put milliamps in, we'll get our answer in kiloohms, which is what they want. So put milliamps in, you get your answer in kiloohms. So it's this one here. What is the ideal resistance of this then? So we have 4 divided by 25 is 0.160 kiloohms. And then we've got to find out what the E24 series is to make sure that the current is just less. So we can't pick 160 ohms there. We've got to pick the next highest, so we'll pick 180 ohms there. So that's the same as 160 ohms, isn't it? And that's the end of the paper.